The next speaker is Jimil Seder from Bureau Veritas. And the title of his talk I see in the book and on the slide is Different Analytic Advancements.
Thank you, Dave. Richard. So yes, today I'm going to talk about a couple of advancements in analytical geochemistry at Bureau Veritas. And I'd just like to acknowledge my co-author and colleague, John Carter. So there's two particular innovations that I want to discuss today. One is laser ablation, ICP-MS, and the other is infrared spectroscopy and machine learning. So firstly, I want to talk about laser ablation. And there's a couple ways that we're currently implementing laser ablation right now. And the most common way is through lithogeochemistry or for lithogeochemistry. And basically, it's the ablation of a pre-selected spot on a fused glass disk, so lithium borate fusion. We're using high productivity robotic fusion, followed by state-of-the-art lasers. These are excimer lasers, and then ICP-MS instrumentation. And the result is a quantitative analysis for a very large element suite. And so some of the benefits of using laser ablation is total analysis to trace and ultra-trace levels, and it's basically the equivalent of an 4-acid ICP-MS package. One of the other benefits is that when you combine the laser ablation ICP-MS with XRF, then you get this very, very large dynamic range. And essentially what it does is it negates the need for overlimits. So you can go from, I give an example there of uranium, from the ppb level all the way to the percent level. There's a simplification there because there's only one fusion, there's only one digestion. So normally with lithogeochemistry, you have to do several types of digestion to get all elements that you need. And then on the safety side, it also minimizes hazards and waste associated with nasty chemicals and acids like perchloric and NHF. So where does laser ablation really fit in here? So we have a single acid digestion, which will get you from the PPT to perhaps just lower percent, aquaregia, a little bit higher detection levels, multi-acid or 4-acid, a little higher. Fusion, we're looking at ppm to high percent. And basically, as you've seen here, it's increasing extraction. So as we move from a single acid to the fusion, we're getting more of a total digestion. Of course, that's increasing the detection limits. But the nice thing, as I said about laser ablation, is that especially when paired with with the XRF, you get that very large dynamic range. So we're also using laser ablation for spot analysis. I've given a couple examples here. One is from Ross Large, 2013. Okay, it's not working. Anyways, just what I want to show here is an example of where Ross used pyrite geochemistry in a shale basin to determine whether that basin is likely to be fertile for gold or is likely to be a barren basin. Another one from Sarah Dare et al., 2012, where she looked at magnetite geochemistry and looked at the differences for a iron-rich monosulfide solution compared with magnetite from a residual copper-rich intermediate sulfide solution. And then, of course, we can also use laser ablation for element maps, and that's where you're doing several spot analysis over a grid to produce these maps. It's very useful for element deportment, mineral associations, inclusions, and so on. So now I'm going to switch gears a little bit to talk about spectral analysis. So we have a system here where we are analyzing samples by using a high logger and that's the near infrared and shortwave infrared. And then Fourier transform infrared spectroscopy, which is a much larger, wider bandwidth, and that's the mid to thermal infrared. And this is really useful because it allows us to look at a much greater range of minerals. And which I'll talk about in just a second here. This is what a spectra would look like. As you can see, the high logger is just a very, or ASD is just a very small portion of that entire spectra. And this is typically the type of minerals that can be detected by the two types of instruments. So high logger, of course, are hydrated minerals for the most part. FTIR, that's where you can start to get into the carbonates and the silicates and so on. So once you've got these spectra and you've got, what do you do with it? So you've got 2,500, up to 2,500 data points for the spectra. So how do you make sense of that? Well, what we've done is we've created machine learning tools and artificial neural networks, and those are really big buzzwords these days. And I'm a geochemist. I'm not a physicist, and I'm certainly not a mathematician. So for the rest of this slide, I can't really tell you too much about how they actually come up with these algorithms. But basically, what that allows you to do is to create a model using the spectra and the scan of the spectra plus empirical results for those same pulps, whether it's geochemistry, mineralogy, physical parameters, and then that information, so whether it's the spectra and the empirical results, are fed into this machine learning algorithm. And then what's done there is that determines what that spectra actually means for predetermined parameters that an individual or a group wants to find out. It's not something where, it's not a traditional geochemical or mineralogical analysis where you're getting you've just got an unknown and you get a full scan and a full readout of exactly what's in that sample. You actually have to tell that model what you want to learn out of it. You have to say, I want to know how much FeO is in this. I want to know how much kaolinite is in this sample, and so on. And then you tell that algorithm to build that model. And once you've trained and you've built that model based on your representative samples, then you can take that model and use it to predict for unknown samples. And as an example, you can look at mineralogy, physical properties, or processing properties, or classification, and geochemistry. Really, the sky's the limit. And in fact, we've had some people come ask us if we could even try to model ARD parameters. So anything you want or anything you can think of. And just to give some examples here, what I've got on the x-axis is the empirical data. On the y-axis is the FTIR, and that'll be for the following slides as well. And what the data is showing is the FTIR was done on unknowns after the model was created, and then subsequently the XRD was run after the fact to determine how close we were. As you can see here, for hematite, for goethite, very good. This is for iron ore. Nickel laterites. So very good correlation between laboratory data and the FTIR. Could be element speciation, so in this case FeO. Mineralogy, so cerussite, siderite. And then physical parameters, pulp density compared, it can still tell you something about that. And that's because all of these parameters, as long as these parameters have a mineralogical base to them, then we can usually measure it. And really, where does the value come out of this? And it's more at that process and mine development stage, because that's where things start to get really expensive. Whether it's metallurgical tests, it could be bond work index, it could be mineralogy, any of these things that start to really become quite expensive. That's where we can start to use this type of innovation to bring those costs down. And instead of choosing 1 in every 20 samples and 1 in every 30 samples to do mineralogy, because you need to know how much kaolinite's in your sample, you can do that on every single sample. And I just have a shot here of a paper that was written by John Carter et al., and that was presented in July of 2017, so there's a lot more information there if you want to read more on the FTIR and machine learning. Thank you very much.
Lots of time for questions. No questions.
With that technology used for making discs and then the laser ablation,
Yep.
those elements which are volatile, how do you deal with that?
You can't, unfortunately. So that wasn't quite. I should have been a little bit more specific. That there are elements, of course, mercury, antimony, arsenic, selenium that are impossible to get, and you need to do an aquaregia to quantify those. So volatile elements, such as mercury, selenium, so on and so forth, we can't accurately quantify those with this method because they are volatile, and you will lose some during the fusion digestion. So that's right. In order to get those, you'd still have to do an aquaregia.
But are you working on any alternative technologies for disc making to prevent that?
Well, our facility in Perth actually has robotic disc making. So I was actually at the lab there for the first time last month, and it's really impressive. And I'll show you some photos after. And they can make thousands of these per day. And all that technology and all that development, robotic development, came about because of the large amount of iron ore samples that we received from the Pilbara.